Hello and warmly welcome everyone. My name is Anastasia Ryasanova and I'm a coordinator of that research infrastructure. And it's a great pleasure for me to welcome you all to the webinar dedicated to the ForMAX Beamline. And today I have several specialists who are attending the session. The first specialist who will give a presentation is Alexandar Matic, who is a professor at Chalmers University of Technology. He will give you some kind of tips and tricks and examples for inspiration, why to apply for the beam time and how to do it. Then here I also have with me Kim Nygård, who will talk directly after Alexandar and will give you more insights directly into the ForMAX Beamline and proposal preparation, because Kim is working directly at the MAX 4 facility as a senior specialist and Beamline manager. So basically, yes, you will hear his presentation also. And then together with us today, we also have Linnea Bjorn from Chalmers University of Technology, who is an expert in performing the synchrotron-based measurements. And after the session today, you will have an opportunity to book the time with the specialists if you would like to discuss your proposals and get some help and revision for the preparation of the proposals. So besides contacting Alexandar and Kim, you are also welcome to talk to Linnea Bjorn. And we have one more specialist, Thomas Rosén from KTH, who unfortunately can't join today, but you will be able to contact him also. With this, I would like to give the floor to Alexandar Matic, who will give you the first presentation. So please, Alexandar, great pleasure.
Thank you very much, Anastasia, and thank you all for joining. And I hope we can inspire you, me and Kim, a little bit how to think about the experiments at ForMAX. It's a great resource we have for research on forest-based materials. And when it comes to expertise, I think that Linnea is the real expert here. So I will often refer to her for questions. And also, as Anastasia said, feel free to contact us afterwards if you need any advice for your proposal preparations. So I just put together a few slides, and not knowing exactly what your background is, I start very very general here. There we go. That what we're talking about is to utilize the Swedish research infrastructure MAX 4, situated here. You see on the field in Lund, a snowy day. This is actually a few years ago, but it basically looks the same still. And what we have here is really a world-leading instrument. So this is what's called a fourth generation synchrotron source, and it was actually the first one in the world. And what it means is that we really have a lot of X-rays. So high intensity, we have a small focus beam and high coherence. So we can use this for doing high sensitivity measurements. We can do imaging, and we can also do in situ operando studies. So really looking at materials under relevant conditions and do fast measurements. So to utilize this for let's say forest-based materials research, the ForMAX Beamline and portal to MAX 4 was created, supported by the Knut and Alice Wallenberg Foundation, but also by industry, to put together a beamline, but also to have this kind of work with training, assistance in preparation of proposals, and maybe later even evaluation. And those of you who are working, for instance, at KTH or other universities or RISE associated to research, you can also have prioritized access to MAX 4 through this ForMAX portal. And I think we can come back to how that works later. So if you haven't been to MAX 4, you have actually two rings which produce X-rays, one small here, the R1, and then the big ring here. So at the small one, we have X-rays produced with lower photon energy, so with longer wavelengths. where we can do, for instance, surface experiments and similar. And on the big ring, we have hard X-ray, so high X-ray energy, and this is where we typically can do diffraction type experiments, but also some spectroscopy. And it's on the big ring down here that you have actually, you see the ForMAX Beamline, which is one of 16 beamlines currently online. And if you are not interested in small angle X-ray, small angle and wide angle X-ray scattering or microtomography, which you can do at ForMAX, there are also a whole range of other beamlines that I think could be of interest for your research. So just encourage you to go to the MAX4 website and look what's actually available, because there is a lot of resources. But today we focus on the ForMAX Beamline. So this is a really versatile instrument for research, and it's super suited for forest-based materials, where we have a bunch of length scales that come into play. In fact, you could say it's actually two instruments in one, where you can both do small and wide angle X-ray scattering, but also you can do microtomography. So if we start with SAX and WAX capability, so what you there cover is from, let's say, the atomic structure of the material up to the arrangement of, let's say, fibrils, fibers, and so on. And then to go to even longer length scales, you can then use the tomography capability to directly image parts of your material, the morphology, and so on. The measurements are fast, so we can also do this time resolved. We see one example of that. We can also do experiments under mechanical load, humidity, and so on. And there's even a capability to do rheology, so-called rheosacs, at the same time. So it's really a versatile instrument, but of course, versatility comes with that you really also have to invest in how to design and prepare your experiment, and that's why we are here. So just to remind ourselves what the length scale we study are. So when we talk about wide angle X-ray scattering, we are on the, let's say, interatomic, intermolecular distances. Then we can also go to small angle X-ray scattering, slightly longer distances, which gives us more the molecular aggregation, if we have nanoparticles, interfaces, and let's say towards the morphology of material. When it comes to X-ray tomography at ForMAX, we start from the micrometer length scale and basically go upwards, so you can really investigate what's there in your object. And a very interesting way to combine these methods is to perform wide and small angle X-ray scattering, but scanning over your sample. So in this way, you actually image what goes on the nanoscale, but you image it over your material. And we will see one example of this. So here is if we start with the small and wide angle X-ray scattering imaging, what you basically do is, if this is your sample, you just raster scan over the surface of your sample and take a full small and wide angle X-ray scattering pattern in each pixel, and then you select a special region. You can maybe say, oh, I'm interested to image this peak, which maybe is of interest for you regarding crystallinity. Or in this case, for instance, we were interested in a little bit more the aggregation phenomena, looked in the low Q region here in the SAX pattern. And then we image this over a full sample, which you see here is something like 1.5 millimeters wide. So what we can see on forest-based materials, starting from the small length scales, typically the cellulose crystal structure. Going further, we can look at particle shape, for instance, in solutions. Let's say you have nanocrystalline cellulose, you can maybe determine the particle shape. You can also look at aggregation of particles, structure of fibers, even processing. If you think about rheosacs, alignment of particles or fibrils in flow. We'll see an example of hydration of wood-based materials. And also by recording the full 2D pattern, scattering pattern, you can also see if there is some particular orientation in your sample. So starting with the first example, and this was, I think, Kim can correct me if I'm wrong, I think this was the second experiment performed at MAX 4. And it's really, for me, this is really important to demonstrate this, because it's not some kind of basic physics or chemistry experiments. It was an experiment together with industry. So you see here, we have Linnea at the computer here, and we have Marianne Leby, who is Linnea's supervisor. But the rest of the people are actually from Tetra Pak. So it was performed between Tetra Pak and Chalmers together with Kim and colleagues to really look at their materials, so really applied science. And you can see here that that was a big engagement in the experiment, and everybody was super excited. And what they were excited about was to look at new cellulose-based straws. So you know we have this legislation now. We should replace all plastic components in society, and one of them is the single-use straws. So you want to make them out of biopolymers. This is one of the things Tetra Pak is doing. And the question here was, when we go to this biopolymer material, how is the material influenced when you, for instance, hydrate it, or also by the design? I mean, a key component here in the straw is this part which bends, and how to design it, and how is the biopolymer then influenced. So here we can look a little bit more in detail, and we have a zoom in, and this is actually now a small angle X-ray scattering picture of the straw. You should disregard the bright parts on the surface, because this is just some edge effects, but instead look into the bulk here, for instance, of this straw. So this is a straw made out of a biopolymer, and we are zooming in on the part where we are bending. And you can see here there are two different designs, one with a lot of a very high frequency on the corrugated pattern, and one where there is much less. And here we zoomed in the small angle X-ray scattering region, so somewhere down here, and you can see that there are a lot of inhomogeneities resulting from this, which can be a sign that you actually start to influence the surface of the particles, maybe causing cracks, and particles here are fibrils then. In the bottom instead, one can see a much more homogeneous structure. So this was like a first result they directly could get out from this experiment. A second thing which was of interest was actually to look what happens with hydration of this material, which is of course central for the use of it. So here is the actual material in itself. So this is some kraft pulp, and you can see here pieces containing fibers. So the straw is in itself intrinsically a hierarchical material, a composite, you could say. And as such, with all these, you see there are lots of voids in the morphology, and you have, of course, the cellulose material. It will be very sensitive to moisture and water, and this will impact the stability, the robustness, and the quality of the end product. So this scanning electron microscope image, and when we then later do our SAX experiment, the beam that we will use is roughly the size of this red square, so some 15 to 56 micrometers. So you can see that here, irrespective of where we focus on the material, we will actually probe, let's say, an average structure of our of the straw. So this is how it roughly looked at the beamline. So you have the X-rays coming here from the right, and we have the detector somewhere in the far away in the tube, and the actual samples, they are placed on this type of grid, so you can have several samples at the same time. And this particular experiment was done just in ambient conditions, so 24 degrees. It was at the beamline, 42% humidity, so no variation there in this size. And here there are two pieces of the starting material, and then also one piece of an actual straw. So you see here you can mount then several samples and then do measurements of them, for instance, consecutively. Here is how it could look, for instance, one example of a result that Linnea got when comparing wet and dry samples. In this particular experiment, they didn't have the humidity chamber ready yet. So here the samples were just wet and dry, and then taken. The wet sample was taken out and put in on the beamline and measured as soon as possible. So it's maybe drying a little bit during the measurement. But what you clearly can see is that the two SAX patterns differ a lot. Where the most pronounced thing is that this peak here shifts to lower Qs, which indicate that we have some kind of increased distance. So we have some kind of swelling, and we'll see later that this is then related to changes in the microfibril structure. And typically one of the difficult things, and here I think advice from, for instance, from Linnea and Kim is really central, is how to now interpret your data, because a bump does not make anybody particularly happy. So in this case, the approach was to use a model in literature previously developed by others for cellulose macrofibril materials. And here you see just the mathematical expression for the model. To the right, you see how the model fits to the data, so it fits reasonably well. And what you get out in this case from the model is what kind of changes do I have on the fibril distance, and also do I have a potential swelling of the actual fibrils. And you can see here that after fitting everything from a dry sample to soaked sample, and then different degrees of humidity. And in this case, one could actually keep the humidity by trapping the sample between two Kapton tape windows and having then a saturated salt solution in the bottom of this to keep the right humidity. And you can see then that with increased humidity, you can see that you have a swelling of the fibril, but you also have an increase of the distance between fibrils. So this directly tells you something about the material. Then I think, I don't know how scientific this is, but it's at least a fun example that, of course, you very rarely use water to actually use a straw to drink water, because that's kind of boring, but maybe use it for orange juice. And what was most surprising, at least to me, maybe the others were expecting this, but to me, you can see that there is a big change in the swelling between orange juice and water. And here you can start and speculate, is it the pH or maybe slower diffusion or whatever that is causing it? But you can see that also these kind of things you can investigate, where we see a much more prominent swelling for water compared to orange juice, which I think from an application point of view probably is quite good, that it's more resistant to orange juice. One part which you also accessed here was actually the VAX data, which tells us about the crystal structure within the fibrils. Here we haven't come as far with the analysis yet, because it has been a little bit tricky to interpret everything, but this is just to showcase that we actually could obtain also this data, or at the same time as we recorded the SAX patterns, you also get information on the crystallinity of the material, which is something you can address. Then moving to a second example to highlight a little bit also the tomographic and the scanning part, the scanning SAX part, but then also the microtomography part. I'd like to show you an example of work done by Martina Olsson, another one of our PhD students, on pharmaceutical solid dispersions, where we want to image the nanostructure. So here, the challenge is to understand, for instance, what you do here is you mix a polymer and the drug and you extrude them together. And the question is now, what kind of morphology do you get? Is the drug just homogeneously distributed? Does it crystallize? You can also mix polymers. Here, for instance, we use the phase-separated matrix for the drug. And then, of course, we want to understand how does this phase separation look? Where is the drug in this phase separation and so on. And this is what Martina addressed. In a previous experiment, which was not done at ForMAX, but was done at CSAX in Switzerland, we could first, with imaging, reveal, so the right image here shows different polymorphs of the drug distributed in the polymer matrix, which is a cellulose-based matrix, by the way. And where you can see that there is kind of a swirling pattern, kind of alignment of these domains. And this has to do with extrusion. So you're basically seeing the extrusion direction. So this was done with a particular nanotomography method. And then we wanted to understand, so is this really representative, what we extracted? Because it was a very small sample. So then we did scanning SAX imaging, where we imaged here, for instance, the low Q region over the whole sample. So the color here would basically would represent the radius of gyration of the polymer in this case over a full extruded strand. So a 1 millimeter sample or 1.5 millimeter sample, and you can see that in fact it's quite representative. But then we went instead to ForMAX, because what Martina now wanted to do was to look at formulations in a condition that is similar as when you take a pill, you swallow it, and you have the dissolution taking place inside your body. So this was an experiment done at ForMAX in October 2023. So a very first test. So you can see here to the left, you see the imaging stations, the microscope, which is then recording the microtomography. And then you can move away this microscope, and then you can do SAX. So Martina created a particular setup. You see here, she has a capped on foil, which makes like a tube. And inside she placed her sample, which is this white, small spaghetti-like thingy. And then she could fill the tube with the dissolution medium, with the buffer medium. And then when she filled it, she could start the measurements and then look at the dissolution as a function of time. And you can see here, when you visit Kim, you will have this type of happy users at the experiment. So what actual target is here? You have a polymer matrix, a phase-separated polymer matrix with HPMC, so hydroxypropyl methyl cellulose, together with polylactic acid polymer here, PLA, and the HPMC phase is really hydrophilic, which will, when you add the dissolution medium, it will swell and quite quickly erode away. And then through this process, set the drug free. And you can see here to the right, the drug release response as a function of time. So the more HPMC you add, so here we have 70% HPMC, you have much more rapid release. So by altering these two, the ratio between the polymers, you can actually then tune the release time. And the idea here was to have like an extended release formulation. And this is work done together with Robin Nilsson and Annette Larsson here at Chalmers, and also connected to the Fiber Competence Center. So here is SEM images you can see of two different formulations, one with equal amount of the two polymers, and one where we have a little bit more of the PLA phase. And you can see that actually the morphology changes quite a lot. These images are made after leaching out the HPMC phase. So what you actually see is the PLA phase that is left. To the right, you see the extruded strand. So this is then the formulation together with drug inside, so the two polymers. And then when you put them in buffer, you can see that with time, so these are samples taking after different amounts of time, you can see how the whole structure swells by the penetration of the buffer into especially the HPMC phase. And now the idea was to follow what goes on. Can we do this with X-rays? So we had here our setup. So the sample is down here, X-ray beam coming in from the right. The objectives are just above. And then here you have, if you remove the microscope, you can then do SAX. You have the flight tube for SAX, and you have also the wide-angle X-ray scattering detector. And here a zoomed-in image of our sample again. And to the left here, now we are looking at a slice through our strand. So imagine you have your spaghetti vertically, and you just take a cross-section through it, a cross-section image just through this, like a horizontal slice through it. So imagine you're looking here at the small part of the sample depicted up here. And this is the starting morphology. And you can see that after some 10 minutes, and then after 1 hour, you can really see how we create more and more voids. We are like leaching out polymer from the sample. So now we are on the way to do a lot of image analysis to quantify these changes. This is also an important part of the experiment, is the analysis, where you then have to work a lot with your images. You collect quite a lot of data. It's important also to highlight another thing here when doing X-ray experiments on soft materials, as wood-based materials are. It's that you can actually have quite large effects sometimes of beam damage. And to the right here, you can see an example that after 1 hour of measurement, we could see things which probably should not be there, that we have beam-induced effects. So then, just to sum up, I just want to highlight another capability, which is the RioSAX capability, and this is with Roland Kader and his postdoc. So if you're interested in this, I recommend that you contact Kim, but also Roland. So if you have something where you want to investigate flow properties, but also, let's say, the structure of the material, I think this is a very interesting setup. So with this, just to highlight the people you can contact afterwards, we have Linnea Björn, who's also here in the Zoom meeting, Thomas Rosén, who could not be in the Zoom meeting, but who is also available to help you with proposals. If you're interested in the rheology setup, I think Roland is the go-to person, but also Kim, of course. And then for those who are at KTH, I understand you have a new professor who is also expert in X-ray scattering. So I thought I would highlight Stefan Roth here as well. So thank you very much.
Thank you so much, dear Alexander. Really great presentation. And yes, you're absolutely right. Now at KTH, we have Stefan Ross also with us. So feel free to talk to him. He has many years of experience working at DESI. So yeah, he can also give you some support when you prepare your proposals. I wanted to ask directly the audience who is together with us. If you have any questions, please feel free to ask Alexander immediately. or we can save questions for later. Because we have one more presentation today to hear, and it's a presentation by Kim. So Alexander, thank you so much. Please stay with us. Now we switch to the presentation of Kim, and then we take the Q&A session at the end. I think that will be the easiest.
Thank you, Anastasia.
Thank you.
And Alexander, my job is very easy now
Yes.
after this great presentation. I thought I would just mention a few minor details to fill in a bit around Alexander's talk. And a very obvious first one is where to get information. So the first source of information is always internet. If you're new at, if you've never done experiment at MAX 4, we have a fair amount of information here. Go to www.maxev.lu.se, and under user access, we have a user guide, which will walk you through the process of applying for beamtime, what to think of in preparation for the beamtime, carrying out the experiments afterwards. So that's rather useful. You can also find links then to the homepage of ForMAX, where you have more technical details on what we can provide. Spatial resolutions, temporal resolutions, such things, but also information on how to prepare your experiment if you do it particularly at ForMAX. So please have a look. The second source of information would then be contacting Beamline staff, maybe, and you can find my contact information on our homepage. I always say it's the best thing with these kind of meetings is you see my face, and therefore it's easier for you to contact me if you have any questions. Okay, very briefly about the process of getting beamtime. The main route is what we call general user access, where twice a year we open a call for proposals. You can apply for beamtime. All the proposals go out to external experts who evaluate the proposal based on scientific merit. MAX 4 gets back a ranking, and then we provide access for users based on this ranking. This is a very good deal for users, because if you go this route, you don't have to pay for access. The only thing we ask for is that you publish your results if you have good results. That's our way to pay back to society who is funding us. Companies can also pay for beamtime. They get then faster access. They don't have to publish. Now, the main point here is yes, that there is a proposal deadline, March 6th. I think it's at 1400. And this is then for a period of September to this year to February next year. So there's roughly a half a year lag time between applying for between half a year and 12 months lag time between applying for beamtime and getting access to carry out the experiment. Now this is a bit problematic if you need fast access. And I always say that you should see MAX 4 or synchrotrons as a complement to the other experiments you do. The good thing about this kind of proposal scheme is that you really have to think through your experiment beforehand. And actually the experiments that are carried out are in general very good ones, because the users have thought out what they want to do. They've been scrutinized by external experts. They are of high quality. So it's a very efficient way of making the best use of the beam time we can provide. I should say here, most of our industrial users also come through the general user mode. They collaborate with maybe with research groups at universities, but it's part of building their knowledge base. Okay, so how does a successful experiment look like? Ideal case, you have a problem, or you have a hypothesis you want to test. You come to MAX4, you carry out an experiment using the instrumentation we provide, the methods we developed, and you go home with fantastic results. Reality is, of course, a bit more difficult. We are missing two pieces in that puzzle. You have to translate your problem into an experiment, and that usually requires some experience. And you don't go home with the results, but you go home with a boatload of data that you need to analyze in order to get those results. So just to give you an idea, if you do some sort of time-resolved full field tomographic imaging or very complex scanning SAX-FAX imaging, then you will collect tens of terabytes of data, maybe even 100 terabytes of data. That can be quite overwhelming. So I like to think of it, if I would try to visualize it somehow in a graph like this, where we have two axes. We have the effort needed to translate your problem into an experiment here. On the horizontal axis, on the vertical one, we have the effort needed for data reduction and analysis. And the darker the color, the more effort is needed. Now, if you think of full field tomographic imaging or SAX-FAX in the traditional sense, then they are fairly easy to apply to a wide range of materials, and they are very user-friendly in this sense. So there are no really major issues with transferring your problem into an experiment, but you do have to spend a bit of time on image analysis and or advanced data analysis, as shown by Alexandar. Now, if you then start to think of more complex experiments, and let's take as an example here scanning SAX-FAX imaging. So you focus down your beam, you raster scan your sample through the beam, you carry out a number of SAX-FAX experiments to map locally nanoscale structure. Then you spend more and more time on or effort on the data analysis part. It becomes data management part. If you do 2D sort of microscopy, it's still fairly straightforward. If you go to 3-dimensional, so SAX-FAX tomography, then you have to also include the tomography reconstruction in your analysis. You can even go to 4D and do something called tensor tomography, where you map out orientation of fibrils within your voxel. But then both data management, data reduction, and analysis becomes very difficult. So there's a progression of difficulty there. Likewise, if you think of, for example, of combining techniques, as Alexandar described, if you combine the full field tomographic imaging and traditional SAX-FAX, then then the effort in data reduction and analysis is not so different from the techniques themselves, but you do have to spend more time and effort on combining these techniques because they are not always mutually compatible. If you go further, like Alexandar showed, sort of some in situ or even in operando combined experiments, then there are lots of details you have to think about in planning that experiment. If you do that by combining full field tomographic imaging and scanning SAXVAX instead, then the effort or the with translating the problem to experiment is no different from the standard SAXVAX counterpart, but again you have to spend more time on data analysis. So the take-home message here, I guess, is we can combine techniques to get fantastic possibilities of multi-scale structural characterization in situ, but it comes as a cost of the effort one has to put in those experiments. And if you think of these combined scanning SAXVAX experiments that Linnea are doing, or the sort of in situ or in operando combined experiments that Alexandar are doing, then so far it's mainly expert users who carry out those experiments because they are very difficult. So to get back to the puzzle I was showing, I always encourage people to collaborate. For a successful experiment, you need at a synchrotron you need first of all you need very good samples, and you need the expertise on that side. You need the expertise on the X-ray side, X-ray methodology side. You may want to do some parallel experiments, like for the RioSAX experiments that Alexandar was mentioning. And you need to get all of these together to have a really successful experiment. And nobody can do all of these by themselves. And I think collaboration is key to really taking an advantage of these kind of instrumentation. Okay, finally a few words about proposal submission. On the MAX4 homepage, in the user guide, you can follow step by step how to submit a proposal. If you apply as a research member, there you can tick in a box that you're a research member, and then you will fall under this quota of guaranteed time, access time for research members. What happens then is that your proposal will still go to the same review panel to be evaluated. The review panel doesn't know who is a research member and who isn't. They'll just make a ranking, but then the allocation of beam time will be done such that to ensure that at least 50% of the beam time is allocated to research members. The main part of the proposal is a 2-page proposal where you explain what you want to do, how you want to do it, and why it's important. And there are templates on MAX4 homepage for the proposal. Now, just a few words, mainly feedback that we gotten from our proposal review committee. If you think when you write the scientific background, I urge you to keep it general. Our reviewers are very experienced and knowledgeable, but most probably they are not working in exactly the same field as you. So you probably don't want to go too much into details in the scientific background. Then, when describing the experimental method, you do need to provide enough details that, that we can carry out a feasibility test. The way it works is that once we gotten the proposals, Beamline staff check the proposals for feasibility. Is it possible to carry out this experiment at, in this case, for ForMAX? And if you don't provide enough sufficient details, then we can only state that in principle possible, but details are lacking, and this is probably not looked at advantageously by the panel. What the panel specifically want is that you briefly outline how you will analyze the data. And this is a way for you to show that you can handle that part of the experiment. And often then it is advantageous to include preliminary data. Finally, the panel wants to see progress in your research. So if you are applying for a second beam time or experiment on the same topic, then they do expect you to show that you got these results, but in order to progress with your experiment, you need, with your research, you need to carry out a second experiment where you then would address some certain questions. Likewise, if you haven't done a synchrotron experiment so far, it's probably advantageous to mention why you need to carry out this experiment, how it furthers your research to date. Very good. Now, in writing a proposal like this, there's also a lot of to think about in terms of what to include in the proposal, how to phrase yourself, what a bit of a jargon. So I would say it's always good to either talk to an experienced colleague at your department or contact Beamline staff. We're happy to provide feedback as long as we get it, let's say, at least a week before deadline. The last few days tend to be rather hectic. Finally, and I already mentioned this, it can feel a bit tedious to write the proposal, but in the end, it does improve your experiment a lot. And I would say the net effect is very much positive. Okay, those were my few points. I'm happy to take questions.
Thank you so much, Kim. Thank you. Thank you for the great presentation. And let me see if I can do like this. Yes, so we have it more as a discussion. Do you guys have any questions, you who follow us online already now? No, not right now, but I know that you guys who participate in this meeting, you already have worked with the beam time, so you are not the beginners completely. And I totally agree with Alexander and with Kim that, yeah, plan your research and try to ask for help if you need any, and please ask for help not a couple of days before the deadline. So that's why we organize this webinar a little bit in advance, so you get the time to talk to the specialists if it's needed. Linnea, do you want to make any comments to share your experience in a couple of words?
No, it has been very nice to do experiments at ForMAX, so I really enjoyed it.
That's great. Thank you so much. I can see also Eskil is together with us, and yeah, I know you did the great work together. So please keep on working towards the same direction. I think with this, we are ready to finish for today. And you have received information for yourself, and this webinar will be available online on the Research YouTube channel. So please share it with your colleagues, and please review it also later yourself. And if you wish to contact one of the specialists, please just do it to book the separate time specifically for the discussion about your proposal or any challenges that you have. Yes. Thank you so much, Alexander, Kim, and all the other participants. Yeah, I can see that Eskil is making a clap. Thank you so much, Eskil, also. Yes, and yes, thank you so much, Alexander, Anna, and Maria also, and Konrad. Yeah, stay tuned. We will have more webinars in the future, and I'm wishing you all a great continuation of the day.
Thank you. Bye.